All right, so let us begin our discussion for today. In the previous class, we discussed about something called EK diagram. EK diagram basically means, let me write it here. So EK diagram basically means that how you are going to define an electron's energy and its momentum. Okay, like how fast it moves. So just to remind you one more time, if I think about the classical particle, a classical particle always follows the following relation. The energy is p square by twice m. P is the momentum, right? So if I draw the energy versus momentum, or let's say the velocity, we can also write P as mass times velocity. So if I draw energy versus momentum of a classical particle, it will look like a parabola, right? And then we know that in case of quantum particle, energy is also related to momentum with the following relation. Same equation. The only difference is that now momentum has a relation with the wave vector k. So we write P is equal to hk whole square. So k is the wave vectors, like how the wave function of electron varies over space. That defines the value of k. If it varies very fast, for instance, let's consider two different waves, one moving very slow and one moving very fast in space, then the faster the variation, the bigger the value of k. Okay, so like classical particle, we can also describe the state of a quantum particle with the EK relation, and we wrote it like this. K is in the x-axis, E is in the y-axis. So in case of a free electron, when the electron is not bound to any atoms, EK relations looks like a parabola. In case of bound electron, so that means if I have a potential well and electrons are all bound within the well, we know that the wave function cannot be arbitrary, right? It must abide by some certain discrete value. So this means the value of k, unlike in a classical particle, in a bound electron, the value of k is always discrete, and so is the value of E. So for a bound electron, if I try to draw the EK diagram, then how should I draw it? Remember that a bound electron only takes some finite value of k. For instance, the value of k, which is 2 pi by lambda, we know that lambda can only be an integer multiple of 2is L, where L is the width of the quantum well. So if lambda is discrete, k is also going to be discrete, right? And if k is discrete, we know that E is also going to be discrete because of this relation. So if I draw the EK diagram, it will look like this. We will have some certain discrete points, okay, that abides by the quantum rules. Okay, so it is still parabola. If you eye gauge, you will see still that it is forming a parabola shape, but not all the points on the parabolas are valid points. there are some discrete points which are only valid. Okay, the discreteness comes because of electrons being bound by the potential wells. And in the second case, when we do not have finitely bound quantum wells, but we have some finite bound quantum wells, and we have multiple quantum wells. So in those cases, we have seen that the energy states, they are going to interact because of the tail of potential. So this is one wave functions, this is another wave functions, another wave functions. All these wave functions would interact through their tail. And because they will interact, the energy would split. All of them would interact. I hope you remember that the higher energies would interact much more compared to the lower energies because the higher energy have bigger tail. So because of higher interactions, these higher energies would split much further. And also, once you consider many quantum wells, all in series, then the eventual state of the electron would look like the following, that they will consist of some bunches of energy states. Okay, let's say we started with a single potential well with two energy levels, and then you add up a lot of quantum wells. Periodically, you will see that instead of having just two energy states, now they will have two bunch of energy states. Okay, and in between this bunch, there is a certain gap which are called forbidden energy gaps. Okay, if I try to draw the EK diagram for these quantum wells, these periodic quantum wells, you will see the EK diagram looks like this. Okay, so this is K and this is energy. So you see that E and K remains continuous. Why? Because I assumed that now we have infinite number of quantum wells periodically arranged, and because of infinite number of wells, the number of energies in each bunch is infinite. Okay, so that means there are continuous energy levels within each bunch. So this is why E and K take some continuous shape within a certain range, as long as you bound the value of K between 0 and pi by L. Remember, L is the periodicity. Okay, so L is the periodicity. And right at the point when K reaches pi by L, you will see that energy takes a big jump. So in between these two different energy points, there is no energy which is allowed. Okay, these are the energy gaps. Same thing is here. These are the energy gaps. Okay, and these are symmetric. So these are the EK diagrams for a periodically arranged quantum wells. And instead of drawing it like this, people draw it in a folded fashion. So they draw it like this. So this is the first branch of EK diagram. Then in the second case, when you have this guy, we can actually translate it by a factor of 2 pi. Okay, why? Because if you look into the Kronig-Penney model, if you look into Kronig-Penney model, from where we got this EK diagram, you will notice that the equation that governs EK diagram, it contains a term of cause kx. Okay, so since it is a cosine function, and cosine function is periodic over a value of 2 pi n, that's the periodicity. So this is why we can always translate any branch of EK diagram by a factor of 2 pi. Okay, so if I translate this guy by a factor of 2 pi, I can bring it here. I can bring this guy here. So instead of drawing it from this point, I can draw it here. And same thing can also be repeated for all the other branches. For instance, this guy, which expands from minus pi by L to minus 2 pi by L, I can translate it by a factor of 2 pi to its right side, so that this guy can be translated and brought back here. So this guy would look like this. Okay, so eventually all of these branches, all of these discrete branches could be transferred back to a region where k is confined by minus pi by L to plus pi by L. Okay, so this is called the reduced EK diagram at reduced Brillouin zone. Or in short, sometimes it's called just reduced EK diagram. Okay, reduced EK diagram. So bottom line is, we can draw EK diagram within only minus pi by L to plus pi by L. And all the things that is important for us is already captured by this diagram, because what we care about the energy gap, which is here. Okay, so this is the energy gap, and these are another energy gap. Okay, these are all different energy gaps. So with that, this is pretty much what we discussed in the previous class. So now let's see that how we can build on top of this. Basically, we're interested to find out that how current conducts in a crystal. So we'll draw EK diagram, and so this is one branch and this is another branch of EK. Now let us say that we start to fill up all these states by electrons. Okay, so filling up the states, if you start to fill up the quantum states, then the first electron will go to the very bottom of the states. Okay, it will take the lowest possible energy states. You bring back another electrons, another pair of electron, it will go to the next higher energy level. The third pair of electron, it will go to the third level, fourth level, fifth level. So this is how the more electron you bring, the more you will see they are going to capture the available states. Okay, so now let's say in a silicon, let's talk about silicon. A silicon has 14 electrons on its atom. Okay, and the way they're distributed over different orbitals is this. It's distributed like 1s2, 2s2, 2p6, then 3s2, 3p2, right? So this is how the electrons in a silicon atom is distributed. Okay, now let's look at the first guy. This branch, these orbitals can accommodate as much as 10 electron. 2 electron can be accommodated by s orbital, and p orbital can accommodate 6 electron. So this is how we get 10 electron in total. So these states are already filled up. Okay, and if something is filled up, then it does not really contribute to electron conductions. Okay, and we said we can see it from these EK diagram also. Let's look at here. If we think about all the states are occupied by electrons, then if you apply some bias voltage, then in order to move the electrons, let's say I want to move this guy, this electron from here to there, but I cannot move it because wherever you want to take it, you will see that another electron is already sitting in that position. So unless you get an empty seat, you cannot really move an electron, no matter what bias you apply. Okay, so this is why all the orbitals at this state are not contributing to current. Now, how about these other states? 3s2, 3p2. So as I said, that p orbital can accommodate total 6 electrons. Okay, so it can go up to 3p6, but it is only up to 3p2. So this means that these guys at the outermost shell, they might have some empty states. Okay, they might have some empty states, but whether the empty states would be occupied by the electrons or not, it depends on some certain factors. For instance, if you, let's say you start with EK diagram that looks like this. This is the valence band. And this is the conduction band. And you started with a situation where all the states are filled up by electrons. Now you do this. You apply some temperatures. If you apply some temperatures, you can excite some electrons from lower valence band to upper valence band. So some electron, because of excitations, they can go to the upper state. So you will see that some electrons, they will jump into the higher energy levels. Okay, and when it jumps, it must leave some empty space from where they jumped. So let's say an electron, previously it was here in the lower valence band, and now because of applying some temperatures or heats, it goes to the higher energy bands. So we have some empty space here. Okay, so this is some empty space. And interestingly, if you have some empty space, those empty space might help you to conduct current. Why? Because remember that in a natural, in a normal case, when you have all the energy states filled up, you have equal number of positive K states and equal number of negative K states. Do you remember that K is actually related to the momentum P by H cut. So mv by H cut. So positive K means positive velocity and negative K means negative velocity. So if I have both positive and negative K states filled up by electrons, that means there is no net velocity of electrons. There are actually equal number of electrons going from left to right and the equal number of electrons going from right to left. But if you can create an empty position, then it might be possible to excite some electrons. Let's say I can excite this electron to go into here, okay, and to fill up that space. But if an electron go here, then it will definitely create an empty space. So this is the new electron. So this is the new electron's position. But now, by moving the electron to a different state, it keeps an empty state on the previous position. And that empty state might be taken by another guy, by another electron. Okay? Maybe this electron will move to these empty states. So it will actually create a chain of event where each electron can move from one seat to another seat. Whenever it will move, it will keep an empty state. That empty seat would be taken care of, would be occupied by another electrons. Okay, so this chain process can create a current conductions. Same thing can be talked about for the conduction bands. Remember, in the conduction bands, I created some electrons by applying heat so that some electron can go from low energy states to upper energy states. So if some electrons are available at the upper energy states, let's say in the EK diagram, this was the EK diagram, and we were able to excite some electrons in the upper energy states. Now, look at that, not all the states are occupied by the electrons. Because not all the states are occupied, if you apply some bias voltage, you might be able to shift some electrons from negative K states to positive K states. So maybe you can shift this guy to positive K states. So you will have more positive K value. That means your current may go even higher. Okay. So two important things here. First of all, current will only conduct whenever electron will find some empty space to flow. Okay. So this is something which was completely missed in the classical analysis. In the classical analysis, there is no concept of empty space or filled up space. Okay. In classical case, if I ask you that, tell me why a copper is so conductive, but a wood or a glass is not conductive. You might say that, well, a copper has a lot of electrons. Glass has no electrons or no free electrons. So that's how we define in the classical sense that how the current conductivity depends on material. But in quantum case, now your understanding is more refined. Now you know that it's not really about having an electron or not having an electron. It is possible that a material have electrons, a lot of electrons, but it will still not be able to conduct current if there is no empty states for electrons to move on. Okay. So that's one big thing that makes a difference between classical descriptions and quantum descriptions. Okay, so keep this in mind. One more time. In order to conduct current, first of all, we need to make sure that when an electron moves to different states, that state must be empty. Okay, because electrons, no two electrons can take the same state. Okay, so very important difference. And the second thing is because of interactions between two energy levels, we can have an energy splitting. So if I have many quantum waves arranged periodically, we might be able to create a bunch of energies. Each of these bunch will have some certain energy gaps. Okay, so until you excite electrons to go from lower bunch to the higher bunch, you may not be able to see any current. Okay, so if all the, let's say, in the valence band, all the states are already taken away, already occupied by electrons. So there are electrons, but because nothing is empty, this valence band won't be able to contribute to current conductions. You might be able to conduct current if you excite some electrons from the valence band to the conduction band. So heat generations is one way by which you can make a current conduction, by which you can excite electrons to go from low level to upper level. Okay. There are also some other opportunities. For instance, you can actually create light. Okay, you can excite a material with a light, and you can see the current conducting goes up. In fact, when you apply some light, the electron can absorb some energy from the light, and it can go from valence band to conduction band. Okay, you can also apply some bias voltage in order to excite electron to go from valence band to conduction band. So all what we are trying to do to make something conductive is to create some empty states, okay, so that electron can flow. All right, so so let me write it down that in order to conduct current or electricity, first of all, we must create an imbalance between positive K and negative K states. Because positive and negative K means positive and negative velocity. So unless you have some imbalance, your net current must be zero. So that's one thing. And in order to create that imbalance, we must have some empty states where the electron can move. Okay, very important. So please bear this in mind. Empty states, the role of empty states. And the third thing is I say that you can excite an electron to go from lower energy level to higher energy level, right? By applying heat. So tell me the following. If I take a copper wire, just a normal copper wire, no quantum mechanics is involved here. And if I increase heat, do you expect the copper wire to increase its conductivity or lose its conductivity? From your common sense, not from this course. Okay. I'll ask again. Do you expect the copper would increase its conductivity or lose its conductivity in case I apply heat? What do you think? Would it be more conductive? It will lose its conductivity, okay? And the descriptions, like general explanations from classical point of view, is that when you apply heat, electron starts to bounce too much, okay? Bounce with atoms. Because of this bouncing back and forth, electron cannot move really well from one end to another end. So that's the classical explanations, okay? In case of semiconductor, if you notice the conductivity of semiconductor, you'll see that it's a function of temperature. And if you increase temperature, it increases the conductivity. Okay. So that's very surprising thing. It really does not match with your classical understanding. Classical understanding says that whenever you increase temperature, electron starts to bounce like with the walls, and it should not move as well as previously. But in semiconductor, we know that applying temperature actually helps to increase conductivity. So there was no classical explanation unless you go to the quantum explanations, which says that actually when you apply some heat or temperature, you are helping some electrons to get excited from valence band to the conduction band. Okay. The more temperature means more electrons will be leaving the valence band and reach the conduction band. So whenever electron leaves those band, remember that electrons are creating some empty states. Okay. So this is why only quantum explanations can explain that why increase of temperature helps to increase the conductivity of semiconductor material. Okay. So I'll write it here. Increase heat will increase conductivity of semiconductor. All right. So these are the very important things. Okay, please keep this in mind. And by the way, I uploaded 2 books in the Canvas. One book is written by Banerjee and Streetman and Banerjee. The other book is written by Professor David Nieman. Sorry, Donald Nieman. Both books are good. Okay. So you can follow either of them. Okay. For some cases, I find the explanation of Donald Nieman more friendly. Okay. So take a look at both of these explanations of these books. Okay. And see that which one you feel more comfortable with. But bottom line is that do not just rely on class materials. Go to the book and try to consult with the stuffs. So now, with that being said, let us talk about a very, very important topic, which is called the effective mass of a particle, of an electron. Why effective mass is important for us? Let's think about the classical picture first, and then we'll see that how mass is important. So if I apply a force, I know that a classical particle will get accelerated. Now, how much accelerations will there be depends on its mass, right? If a particle has a very big mass, it won't try to accelerate, right? It would accelerate less. A particle with a lighter mass would accelerate much faster. Okay, it's because Newton's law says force is equal to m multiplied by a. Okay? Likewise, in a quantum description, we can also use Newton's formula in order to find out that how an electron is going to be accelerated if I apply some bias voltage. Okay. So you may say that, well, I know the mass of electron, and how about the force? Remember that the force, in case of bias voltage, force comes from the electric field. So let's say you take a 1-volt battery. So 1-volt battery would actually create 1 electron volt of energy. Okay. So let's say I take a material, okay, let's say copper material, okay, and I apply a bias voltage, let's say 1 volt, okay. Let us say that this copper wire is 10 millimeter long. So what is the force here? What force do I apply on the electrons? You can calculate the force like this. Force is equal to the electric field multiplied by the charge of electrons. So electric field can be figured out by taking into the account that voltage and dividing them by the length of the wire. So in case of 1-volt voltage, we can calculate the force like Q is equal to 1.6 10 inverse 19 coulomb. Let's say your battery is 1 volt, your copper wire is 10 millimeter long. So just plugging in this number, you can find out the corresponding value of the force, which is, well, here something like 10 inverse 20 Newton. Okay, so we can say that, well, it looks pretty simple. So if I just say that, okay, instead of copper, why don't you just use a silicon material? And let's say the silicon material have the same dimensions, 10 millimeter long silicon wires. You apply some bias voltage and 1 volt bias voltage. So I can find out the accelerations because I know the force. I can easily calculate like using these formulas. And I know the mass of electron. Mass of electron is something like 9.1 10 inverse 31 kilogram. So maybe I can find out the accelerations of electron very well. Unfortunately, this won't work. Okay, this won't work at all. And the reason is, it's not really the problem with the force. Force is probably okay. The problem is with the mass. It's true that if you somehow isolate an electron and try to measure the mass, you'll see this value 9.1 10 inverse 31. But in case of electrons moving in a crystal, this mass is very different. Think about this. Let's say I take a particle of 1 kilogram mass, I release it, it falls ground. You can find out the corresponding accelerations. Now, if I do the same experiment in water, okay, I let this guy fall through the water and I use the same value of mass. Will I have the same accelerations? No, because this time I changed the system, right? When it goes to the water, it actually it collides with the water atoms, like water particles, and it changes its velocity, right? So when you change the medium, you have to take into account all the interactions that is going on between the particle and the medium. Okay. Now there are two approaches. One approach is that you take into account that how exactly water atoms is bombarding with the particles to reduce its speed. The other way is simpler. It is that, let's say, whenever you think about a particle getting dropped through the water, you will, instead of using the exact mass of the particle, you will use a reduced mass, a new mass of the particle. Okay. So if you can somehow find an effective mass of the particle, you can forget that whether it is getting dropped to the water or not. You will just use that new mass in order to find out the accelerations. Do you follow that? What is the strategy here? So the first option is more rigorous, but it is very difficult to do if you try to take care of all the interactions that is happening between the water atoms and the particles. The second one is much easier, which says that I'll forget about the water. I'll just say so that somehow, for some reason, the particle has a lower mass. Okay. And that's why the acceleration changes. So we apply the same idea here when electrons tries to flow through a crystal. Okay. Oh yeah, we have just 2 minutes. So remember that when electron moves through a crystal, and how electron moves through a crystal? By doing the interactions to the tails, right? And after taking interactions into account, you get an EK diagram. You get an EK diagram. Okay, this is your EK diagram. And K basically gives you the velocity, right? So you can use this EK diagram in order to find the effective mass. How do you find it? Well, let's start from this expression. In case of free electron, In case of free electron, I know my EK diagram would be just a parabola. So let us just write it. E equal to hk square divided by twice m. Now I can do this. I can take first derivative of energy with respect to k, which will give me hk, actually twice hk by m. So that would be my h squared k, sorry. So that would be my first derivative of energy. Sorry, the bell rings. I just said it to remind me that the class is over. Yeah, I really is like going beyond the class. So please just allow me one more minute and then we'll wrap up. So if you take the second derivative of energy with respect to k, you will get h squared divided by m. So now look at that. We can say that mass is actually h squared divided by 1 over the second derivative of energy with respect to k. Okay. So this actually gives an idea that I can calculate if I know somehow the EK diagram. By using this EK diagram, I might be able to know what is the mass of electrons. Okay. So you know that this EK diagram, it actually depends on few factors. For instance, what are those atoms that you brought close to each other? How close you brought those atoms? And for instance, if you bring the atom very close to each other, then the interaction would change, right? If the interaction change, EK diagram would also change, and that changing would also impact its mass. Okay, so in the next class, we will see that how effective mass can be extracted from EK diagram. Thank you, guys.